Okay, so let's start. So this is the session on quantum gravity phenomenology, and today's first speaker, it's a real pleasure to introduce him. So that's Giovanni Amelino-Camelia from Naples, and he has been working on quantum gravity phenomenology for a long time, and maybe he was one of the first people to develop the subject. And he has contributed to issues like the minimal length scales, which in quantum gravity, and using observations like GRBs to probe quantum gravity. And I remember one of my very first talks that I heard on quantum gravity was more than 20 years ago. And the talk was titled, Are We at the Dawn of Quantum Gravity Phenomenology? And I think today the title is very much the same. So with that, let's look forward to the talk. And Giovanni, it's all yours.
Okay, can everybody hear me? Yes. Also remotely, yeah? Can you hear me?
Yes, we can hear you.
Good. So it's better. Do you have a way to tell us that they're not hearing?
But there's a chat. There is a chat.
Okay, and who's
And,
checking? I was on this other check. Okay, thank you for the introduction. And so, yes, it was indeed. We are on this side of the conference. We are, in some sense, celebrating the last annual meeting of this cost action, which was a lot of fun. And so I thought, well, for me, it was an opportunity to think over these now more than 20 years that make me feel very old, of course, and what happened to quantum gravity phenomenology. When I gave that talk, it was at the Carpatch Winter School in 1999, and I gave it then several times over a couple of years. The field was really just starting, and it was in some sense even difficult to explain the idea. The background was the feeling about quantum gravity that was widespread up to that point. I always have, I mean, somebody I really looked up to in those days was Chris Isham. We actually worked not far from each other for some time. And however, Chris nicely captured in one of his reviews the feeling toward the phenomenology that was widespread in quantum gravity in those days. But then we started to see some opportunities for at least testing plausible, however, vaguely plausible, but plausible effects that might come from the Planck scale with Planck scale sensitivity. And much more, I mean, one thing I can say, everybody can discuss whether we did a lot or little, but I can tell you that we did much more than I imagined over these 20 years. And in those days, really this idea that the phenomenology for quantum gravity could start was based on just first very heuristic or at best semi-heuristic estimates of effects. Now we have actual derivations of effects in quantum space-time toy models, like Kappa-Minkowski. And we have, as part of my presentation, I hope we'll at least hint at, we have rather mature phenomenological models for effects. So I would say over these 20 years, what I imagined in those days, I imagined that this phenomenology, this bottom-up approach, this idea of a quantum gravity research, which also starts from the bottom, whereas in those days, the only idea was to start from the top, to be very lucky and make the right guess about quantum gravity at the Planck scale, and then maybe one day come down from this fantastic intuition to phenomenology. And in some sense, one of the ideas was to create some, direction of advancement from the bottom so that the trip would be shorter. And I'd say from what concerns phenomenology and the needed contact with observations from early science, I mean, the bottom-up approach has done pretty well considering the challenges for these 20 years. Still, it didn't work fully, the idea I had in those days, because from the top, it's still very hard. I mean, people got interested, but it seems that the theories are too complex, and some, you will see some examples of the questions that phenomenology needs answers for. I mean, these questions appear to be still not within the technical grasp of what I call top-down approaches. And in these 20 years, quantum gravity phenomenology is now a very broad field. The number of, this is also totally unexpected with respect to what I was imagining 20 years ago. In spite of the fact that everybody's reference still is in-vacuum dispersion, and for some people, in-vacuum dispersion is all quantum gravity phenomenology, it's actually a very broad field. I will talk about in-vacuum dispersion is still the kind of benchmark for the progress of this phenomenology, but the number of opportunities that have been discovered over these 20 years is impressive. A pretty wide list is in my review, and even just focusing on astrophysics in this multi-messenger area, those who have not followed will be pretty impressed by the list of opportunities and the type of careful work that has been done both on the phenomenology theory side and on the observation side by, in particular, people in this cost action. And the review we produced is now, I guess, a rather good reference. So it's very broad. I have, however, 4 things on my menu today, which 3 of them are among the topics which were most discussed in this cost action. And the in-vacuum dispersion, again, which I will discuss, however, in rather powerful language of dual curvature redshift. Then there is dual curvature lensing, which is a companion effect, another propagation effect. Then I'll talk about threshold anomalies, which is also very interesting for astrophysics. And in the end, I'll talk about, since the action is finishing, I should have an item outside the scope of this action, and I will talk about IR-UV mixing, which has not been for the kind of phenomenological opportunities it provides, was not one of the focuses of this cost action, but maybe surely an important topic for other collaborations. And so let's start. Quick review of in-vacuum dispersion, which was kind of the first idea that really made it clear that for some effect you could conjecture for the Planck scale. There was data of a quality sufficient for testing it, and it's also historical. In those days, we have here Nick Mavromatos, and we were working on this in the dark rooms of Oxford University to begin with. And all we had was some semi-heuristic argument pointing to the idea that in a space-time that was macroscopically flat, there might be an imprint of quantum properties of space-time, which would amount to a time of travel anomaly of this order. Essentially, the typical phenomenological estimate, some power of the ratio of the energy over the Planck scale. And we realized that some astrophysical sources had time inequality. If we remember, beginning, we didn't know about the GRBs being so distant, so we focused on pulsars, for example. Remember, there are many types of astrophysical sources that are in some sense, in a very general sense, very good clocks, very far away. And so then we were very lucky because a few months later, it was discovered a gamma ray burst with the Beppo-Sachs observation. It was discovered gamma ray bursts were much farther than astrophysicists had conjectured for a long time. So it was perfect timing for us. And we got rid of the pulsars, which were very hard to analyze, and we got to the gamma ray burst story. And it's a race. You want to test this idea, it's a race. So you need a good clock far away. A good clock means something which has a time scale quality. And gamma ray bursts have all the nice properties you might desire, with the exception of one. This is fundamental physics where the laboratory is the universe. And so it's not a prepared experiment. For like someone like me coming from particle physics in part of my interests, it's still the ugly word of astrophysics. My friends here will forgive me for saying this, but it's just that it's perfect, but it's not a laboratory experiment. So you deal all the time with a sort of uncertainty about the outcome, which has not to do with the quality of your data, but the quality of your understanding of the source, which you do not control. But this is also very fascinating. I mean, to have this fundamental physics in which the universe is the laboratory is perhaps on a broader conceptual scale, a significant accomplishment for this type of, the usual direction of fundamental physics, the physics that studies the more and more microscopic scales, is to adapt very strongly to the very big and unknown features of the whole cosmos. So that has been a journey which we're still doing and fighting. So I will not give detail. There are a gray part on this slide because there are some technical details which I'll omit, but there are questions I can show. But for the understanding of in-vacuum dispersion, I guess a very useful tool, probably nothing more than a tool, but surely very valuable, are these works on the relative locality framework, where we realize that some of these models where you find in-vacuum dispersion actually were all models where momentum space was curved. And momentum space was curved in a certain technical sense, which again, I will not describe, but I can describe in answer to questions. But it's very interesting that these allowed us both a conceptual understanding, but also technical advantage. We now compute what we call sloppily time delays. We compute the time delays as dual redshift, as I mentioned. And for those who are not quickly seeing the connection, I mean, just seeing that ordinary redshift in the zeta spacetime is such that particles emitted with the same energy but at different times reach the detector with different energy. And what we find is just exactly a dual picture. So, for example, dual redshift in the zeta momentum space is such that particles emitted simultaneously but with different energies from a distant source reach the detector at different times, which is in-vacuum dispersion. So this was conceptually a useful tool, but still it was flat space-time. Okay, when I say dual redshift in the zeta momentum space, we are leaving implicit that we have a good understanding, we have good formalisms to handle this. If we assume that space-time is macroscopically flat, and also the formulas Nick and I were using in the old days are flat space-time formulas, but the gamma ray bursts are in our universe, which is not flat. So technically, one of the challenges that has kept us more busy, those studying about dispersion for these 20 years, is to understand how these results, if we use the relative locality framework, some of these results are absolutely clean and rigorous when you assume space-time is flat on macroscopic scales, but how these results are changed if you work in a curved space-time. And to deal with both curvature of space-time and curvature of momentum space, together is really a mess, even from the point of view of just developing phenomenological models. It's very hard. We discovered it was a conjecture. Max Born in 1938 already conjectured that this might be needed for quantum gravity to be able to deal both with curvature of momentum space and curvature of space-time, but that somehow mystical encouragement does not provide the tools to handle it. The phenomenology has managed to make progress thanks to, well, preliminary work by Nick Mavromatos, John Ellis, and others, but most efficiently in some work by Jacob and Piran, where with a compelling heuristic argument, they produced a formula for how basically this energy-dependent time delay would interface with the curvature of space-time. And most phenomenology, 99% of data analysis, for example, they all use this Jacob-Piran formula, which actually is proving to be more powerful than even initially imagined. But one of the new challenges for this phenomenology is to understand what are the alternatives. Actually, we do find constructively, I would say, in the SR models, for some models of the curvature of momentum space, you actually find the Jacob-Piran is not heuristically motivated; it's just derived constructively without any assumptions. For some assumptions about the curvature of momentum space, I mean, not assumptions technically, but you have some assumed structure for momentum space, and you just get the Jacob-Piran formulas, but there are alternatives, and this is now one of the, I would say, hot topics in this research line. If you have broken relativistic invariance, you can have the Jacob-Piran formula, but really you can have anything. If you break più vicino, if you break Lorentz invariance, you break symmetries, anything goes. So we are noticing more and more terms that could be alternatives to the Jacob-Piran ansatz. But there is no limitation in principle. You need a specific theory to analyze and derive the effect, but you cannot constrain the form of the redshift dependence using the Lorentz invariance. It's broken because when you break it, it's broken. We have some direction of investigation, which I will say more later, so I will just keep on now, which is the curvature-induced effects. And then we have this deformed symmetry. So if relativistic invariance is not broken, but just deformed, then instead we are discovering, actually Domenico Frattulillo later today here will give a final word on this, because we have the most general DSR compatible formula for the redshift dependence, and we discovered it only has 3 terms, which is worse than 1, but better than infinity. So we will deal with the 3 terms from the DSR side. 2 had already been discovered, but we recently became able to do the most general analysis. So this is one of the frontiers. This is one thing that if you have a favorite top-down approach, assuming there is impactful dispersion in your top-down approach, which will not always be the case, but if you have it, then the real important input for phenomenology will be this redshift dependence. But this will require the top-down approach to be able to describe a physical question like propagate a particle when macroscopic curvature is F of W, because that's where the measurements are. Let me pause a moment on these curvature-induced effects, which are another kind of new frontier, because the Jacob-Piran formula, which has been very influential, as I mentioned, is not of this type. So the Jacob-Piran formula is a time delay formula which gives you a time delay even in the flat space-time limit. Now, from the from symmetry perspective, what we are dealing with is probably a quantum group or something similar to quantum group, but the way we model it is through of algebras, basically. And in order for the effects to be still present in the, so say you have the in-vacuum dispersion in a quantum version of the Sitter symmetries. A quantum group, Q de Sitter could be, some people in the audience here in Rijeka are experts of Q de Sitter. And say you have, as you have in Q de Sitter, you do have in-vacuum dispersion. Now, will you have in-vacuum dispersion in the flat space-time limit of this picture? Well, that is what should come out of an Wigner contraction of this de Sitter type algebra to the corresponding Poincare limit algebra, and typically the contraction of such of algebra is a Lie algebra. So this was stressed in particular in a paper that we did with Artem Starduksev very small in many years ago already, 2004, and where we noticed that most of the arguments leading to quantum groups in quantum gravity, they all had in common that the Q deformation scale, the quantum group parameter, it's not a scale actually, in the quantum group Q is adimensional, but is obtained by combining the Planck length and the cosmological constant, say, if you assume the Sitter is, if you call the parameter of the Sitter, you call it cosmological constant, they combine the Planck length and the cosmological constant in such a way that when you do then the Wigner contraction, the quantum group features disappears. So in this case, you would have in-vacuum dispersion when you have curvature macroscopically, but in a certain form that would disappear in the flat space-time limit. And interestingly, there are other arguments, one more inspired from the loop quantum gravity intuition by Rovelli and Bianchi, also motivate, I would say at a semi-heuristic level, but rather compellingly, that a quantum group parameter Q coming from quantum gravity should be given by this function of the product of the Planck scale squared with the cosmological constant. And in all such cases, you would expect, if you have in-vacuum dispersion, and I repeat, if Q de Sitter arises in your framework, if the quantum group Q de Sitter arises in your framework, chances are you will have in-vacuum dispersion, but it will be of this particular type, curvature induced. So such that in the limit of flat space-time, it will disappear. And we have now some phenomenology of curvature induced, even for the broken symmetry effects. I repeat, the Jacob-Piran is not curvature induced, so we need to find a new reference for curvature induced effects in the broken symmetry phenomenology, which is not easy because maybe it's we should try, because we see only so many terms possible, and so we can give examples, but there must be, once again, one such combination of terms that the expert astrophysicist will look at and consider most deserving of attention. We just are able to analyze this broken symmetry curvature induced effects rather in detail right now. And what Domenico Frattulillo will say later today is that from the DSR perspective, we have a full distribution of curvature induced. The most general formula for DSR curvature induced in-vacuum dispersion, and it is a two-parameter formula. One of the parameters must be set to 0, one of the most general formula to get curvature induced. So this is just an example. I mean, I don't know the broader scheme or broader picture, though this will be perhaps irrelevant, but it gives you a sense of what are the type of issues that phenomenologists must struggle with. I mean, we are in a real universe with its curvature, with its bumpiness, with magnetic fields, and so we cannot use charged particles to do these studies, which would be very useful. And our daily routine is just fighting all these enemies in some sense. I will say very little about dual curvature lensing, but it's just basically the same effect rather than, as the name says, when you have a curved momentum space, there can be some longitudinal, some effects in the direction, in the plane, say in the plane of time and the direction of propagation. And those will be in vacuum dispersion, and those are dual redshift. But when you have a curved momentum space, chances are you will also have dual lensing, and this is an effect in the plane orthogonal to the propagation direction. So what produces are artifacts about the direction. So instead of looking for an angle, in the xt plane, which is time delay basically, you look for an angle in, so it's a misdirection in the yz plane, whereas the vacuum dispersion is misdirection in the xt plane. So it's very similar. The phenomenology was stuck at the beginning for a very long time, because for this you need very accurate directions rather than accurate time. And for astrophysics, accurate directions are there. But I'm hopeful that at least this phenomenology will start now with multi-satellite telescopes, which promise to give us a much better direction in observation of some astrophysical phenomena. So this is just an appetizer, a hint that maybe I keep this long, I'm still alive in 20 years. If I still have voice, I can say that dual gravity lensing did many progress. Threshold anomalies. Threshold anomalies are basically forbidden in DSR. If you deform symmetries, you need basically, it's not that they're forbidden, but you will get them at the scale where you put the new physics. So that's not what we want. We are doing a phenomenology where the scales we access are very distant from the scale which is our target. So let's say that threshold anomalies are just for the broken symmetry, but there is a very interesting phenomenology coming out of it. I remind you quickly how it works. For example, we have some features in astrophysics which are connected to the threshold energy requirement for gamma producing E plus and minus. This is typically when we observe a high energy photon from a distant source, and we know it traveled in the background of cosmic photons, and those background photons are the target to make electron-positron pair. And of course, if you have the unsharpness of the particles being modified, you will modify, I will skip the details, but you will modify your threshold formula for electron-positron pair production in a characteristic way. And this again, it works out to be one of those rare cases where the conjecture plug scale effect is actually observable in astrophysics. And the data situation continues to be very interesting. The most famous threshold anomaly, which has a beautiful history, which also teaches a lot about doing fundamental physics using the universe's laboratory, is the GZK cutoff. There is a similar threshold anomaly, which actually Sui and I studied already 22 years ago. But there was a Japanese, somebody before us did. I'm sorry, I don't have references on this slide, and I should credit a Japanese colleague whose name I'm now not remembering. But certainly, Sui and I put in order these results in 2001. And this is the very big opportunities, because in this case, the cosmic ray protons we observe have energies of 10 to 20 electron volts in some cases and above. And there is a threshold anomaly for the bion production that you can quickly analyze and robustly analyze. And the story of this possible threshold anomaly is very funny, because when Sui and I wrote this paper 20 years ago, there was considered to be lots of evidence for the threshold anomaly. And then at some point, about 10 years later, the threshold anomaly had completely disappeared according to some analysis. And then now it has reappeared again in some sense. So this is the difficulty of the universal laboratory. And so also, if you ask me, I can explain how these big changes are arising. But that's still an open issue. Then we have an opportunity, just to say also to more formal theories, there is a real opportunity. There is something we still need to understand about this possible threshold anomaly. And similar for the electron-positron pair production by photons, which I mentioned before, not only there are opportunities, but the data are going to be of much better quality in the coming years. There are two very different opportunities. There is the one that was most studied over the last 20 years is for TeV blazars. So for photons of, say, 10 TeV, 20 TeV energy coming from redshift of, say, 0.3, 0.4, 0.2, low 0.3, that's where if you use what some experiments, some observations suggest is the levels of far infrared background photons, these 10 TeV, 20 TeV photons should be absorbed by that background, and they are not so absorbed. So that's another kind of small crisis. The universe is less opaque to multi-TeV photons that it was initially assumed. But again, the universe is a laboratory and we don't know who to trust because it's also very likely, probably the most likely explanation. Every other explanation before quantum gravity is always more likely, actually. And the most likely explanation is that the measurements, they are indeed very difficult, these measurements of the far infrared background. So probably the answer is this, that we do not have enough quality of the measure of the far infrared background to actually have robust prediction of how much the universe should be. But there is a crisis. There is something to be understood here, a real opportunity for, it's not just, well, this we can measure. That's where some measurement is not giving so far a nice picture. And similarly with LASO, now we are observing much more energetic photons. The background photons, the background there is much better understood, but the universe is a laboratory, so it happens that when you understand the background, because there is lower energy photons are relevant for higher energy. Lower energy photon background is relevant when the high energy photon traveling is of higher energy. LASO observes at higher energy, there we know the background, but LASO is still not able to find sources. So we don't know from how far we see. But all this is going to soon. Something about infrared ultraviolet mixing very quickly is infrared ultraviolet mixing has not been a topic of this cost action because so far very little implication for astrophysics have been conceived by phenomenologists, but this could be the topic of another cost action, for example, or one of the topics, and surely is a key target for phenomenology, where also more formal quantum gravity researchers could help. It used to be a very hot topic in top-down approaches some years ago. It remains very significant for phenomenology. It's probably a very generic prediction of quantum gravity to have some infrared ultraviolet mixing. If you think about it, Hawking radiation, or actually the information paradox and the fact that entropy scales with area. If you have a theory where entropy scales with area, then you have infrared ultraviolet mixing for sure, because you have infinite ultraviolet features, but you have crisis which goes worse and worse in the infrared. So this should be a very generic prediction of quantum gravity, at least of all models that have entropy scaling roughly with area. And you also find it again in some quantum space-time tau models. You find it now constructively There's a famous story, particularly in the canonical non-commutativity of space-time. The point is that the canonical non-commutativity screws up renormalization, and when you renormalize the theory, you're left with the renormalized theory, which has infrared features, which are very significant. That's a kind of a reference calculation showing how infrared ultraviolet mixing might arise. Why is phenomenology interested? Well, once again, for totally different reasons, but its own shellness is the propagator really that is, at least in this toy model canonical quantum space-time, canonical non-commutative space-time examples, is really the propagator that gets primarily affected by this IR remixing. So again, it's physics with a deformed own shellness that comes from this infrared ultraviolet mixing. But now, of course, the features that you look for are features that pop up in infrared, and there are various candidates for these infrared effects coming from different models. The one possibility that hard infrared ultraviolet mixing has a 1/p² Pole, and that's, you cannot do much phenomenology with it. A pole is not so easy to deal with phenomenology. You just, if no disaster happens, a pole manifests itself as a disaster. So you improve your phenomenological bounds on these forms of infrared ultraviolet mixing by just going at lower and lower momenta and checking that no disaster happens. More interesting are other softer forms of infrared ultraviolet mixing, which I illustrate on these slides. And they have, these are, for example, significant implications for cold atom interferometry that has been shown very definitely. And in astrophysics, these things will affect things like the Chandrasekhar model, where the on-shellness plays a very detailed role. Okay, so this was my menu. Now, let me close a few minutes on this was the menu, and it's a very general perspective, some directions, as I mentioned. The interesting thing of this menu, of course, you have the English version of ogni scarafone è bello ma non so. There is an Italian expression that every ugly person is beautiful for their mother. Ogni scarafone è bello ma non so. This is Neapolitan. And I mean, of course, this just comes to mind, but every speaker will say that what he tells you is very interesting. So I tried to avoid that, but I was just saying that the menu is very interesting because every scarafone is beautiful for his mother, but also because there is something new happening in all these directions. I will close now with the invariant dispersion update, but I mentioned that for dual gravity lensing, really a totally new window is opening, because with multi-satellite telescopes, we will enter a totally new window, and they are going online. So this is coming. And for threshold anomalies, if nothing else, LASO is probably going to revolutionize the field. And for IRUP mixing, if nothing else, surely the cold atom interferometry is one sure bet. If you want to bet, there is a classic law that every field should improve by a factor 10 every 10 years. But really, the only ones who are doing it are those doing cold atom interferometry, and they will keep doing it apparently. So the quality of data for at least that branch of IRUP mixing is going to improve at the pace of a factor 10 every 10 years. You can bet your money on that. So these are all menu items that look beautiful to me, and this might not be very objective, but they are items where improvements are coming in the next years. Let me close with some remarks on where in vacuum dispersion, the more mature, certainly, phenomenology of this sort stands. Well, something that I also didn't imagine. We didn't know really, in 1999, we didn't know how gamma ray bursts at high energies would look like, because we only had, at that point, telescopes which would see gamma ray bursts at much lower energies than the one inferred from this graph. What we have discovered is that some gamma ray bursts, they are really very efficient for testing hypotheses like in evapodispersion. Look at this particular burst. This is a burst from 10th of May of 2009. And there is one particularly energetic photon of about 30 JeV, which we observed in very close coincidence with the busiest. Now, the signal has also a rather busy part between 1 JeV and say 5 JeV or something like that. And the busiest part of the signal between 1 and 3 JeV, say, is very good temporal coincidence with the 30 GeV photon. Of course, the universe is a laboratory, so many things the source could do that would affect what I'm just going to say, but it looks very unlikely that there was evapodispersion at a scale larger than, say, this alpha second scale that we have in the bottom here. It would require a huge conspiracy for that to happen. So from data like this, and we measured the redshift. This particular gamma ray burst, if I remember correctly, is a redshift of about 0.9. So it's we measured the redshift, we know how far it is, and we have some reasonable up to conspiracies, let's say, modulo conspiracies. We have a case that can bound how much evapodispersion can occur. And actually, if you put the numbers, even just very simple, there are more sophisticated techniques that some astrophysicists are using, but if you just limit yourself to this very simple and therefore robust argument, you actually find that you are testing evapodispersion just at the level of the Planck scale in the linear formula, and that's even more than I expected. Something interesting is, well, and I have some others. I mean, this is probably the burst. This burst from 2009 is probably the best, but I have other examples I could show of very similar, robust cases where you don't see the effect at the level close or of the order at least of Planck scale. Actually started with work by the group of Boca and Mahado, but actually already Alice and Mavromatos and others, I think also Dimitri was in those papers, or don't remember you. Okay, I don't have references on some of the guys, but there was whereas some were looking at single gamma ray bursts and trying to make observations like the one I just made. Actually, the first ones were Alice, Mavromatos, and others, but then more determinedly, let's say, a group in China led by Boca and Ma. The idea was, well, this is a redshift-dependent effect, and as we described in our early paper, I mean, the redshift dependence is really the key. We don't know what redshift dependence could be, but we can take as reference the Jacob-Piran ansatz, and let's put. So what in the end, through the work of Boca and Ma and others, became a recent standard for doing this statistical analysis, to take photons which had emission of energy greater than 40 GeV and to plot their delta T with respect to the first peak and low energy of the signal. So it's basically, it take more time than I have to explain in detail, but you're basically putting together different GRPs by only using their most energetic photons, and you look for a correlation. Is actually the data show to some extent. And I circled 2 points because the red point is actually the gamma ray burst from May of 2009, which I was mentioning, and in fact it's off. the correlation. And the green point is important because it's actually a prediction, because when Bokema and collaborators started to make these graphs, that point was not yet observed. So it has a kind of, even so far, very moderate but successful predictivity in this approach. Last item, neutrinos. So finally we have our chairman Julia was on the neutrino analysis. So she just gave me 1 more minute. It was 2 minutes, became 3. Okay. It would just look like a funny joke that the chairman gives you an extra minute.
For citing them.
But she didn't do it. It's just my mind. But doesn't work well. So neutrinos, why now we have neutrinos. That's something I didn't figure out, at least how important it could be. We have neutrino telescopes, and we have robust evidence that we are seeing neutrinos from outside our galaxy, and most astrophysics experts, when I started to realize that observing neutrinos from gamma ray bursts would be powerful for the phenomenology, they were telling me, and the papers were saying that IceCube should see 5 or 6 GRB neutrinos per year. Okay? Some in the audience will remember these predictions. Well, IceCube has taken more than 10 years of data and has seen not a single GRB neutrino. So this is another crisis like the one of the far infrared background. So is this a mystery, or is just that our astrophysical models really are not reliable to the point of predicting how big, how frequently we should observe GRB neutrinos? The answer is obviously, most likely, the models need to be improved. However, there is something to be understood. And certainly, in-vacuum dispersion here could be relevant because IceCube looks for GRB neutrinos by type requirement of time coincidence between the neutrino and the GRB. But of course, if you have a time delay acquired by the neutrinos, you wouldn't see them in that window. So what we did in a series of papers, one appeared very recently in the June issue of Nature Astronomy, is to look for correlation between neutrinos and GRBs, not with coincident time, but with the time of arrival difference governed in this exploratory study again by the Jacob Piran ansatz. And it was kind of interesting as we look at the data that we had available. I should make Giacomo Rosati will talk later today. Tomorrow, you speak. Giacomo will give the details of this analysis, but we find a quite impressive, certainly preliminary, just a few events, but there is an interesting case that we could build, preliminary case, that this idea of looking for correlation between neutrinos and GRBs, but with a time delay, they're certainly not there in coincident times. But if you input the time delay that we could expect from this in-vacuum dispersion phenomenology, then a rather striking correlation arises. And this again, I mean, I will not dwell much on how significant this is correlation. We have statistical tools in our paper if you're interested. In our paper, this of course is described in detail, but really on the topic of this talk, this is another area where we will have much more data. And if, again, you're not bored and I give a talk like this in 10 years, I will be dead. Wow. If you ask me, in 10 years, I will have many more neutrinos on this line. And so this correlation will either disappear or become very strong. And on this, I stop because the chairman just threatened to kill me. For those who are not here, I should relay that there are witnesses that the chairman, when threatened to kill me if I didn't stop. So of course I stopped. Thank you.
Thank you for being on time. And I think we will give priority to questions from the virtual audience. So, Tim.
Which is us, but we can do questions from both places. So we can do questions from both places. So let us start with Madhavan, then here.
Yeah, so I had a question about there was an earlier paper by John Collins and Alejandro Perez and Daniel Sudarsky, and many of these effects which were preferred frame or Lorentz violating, etc., they managed to argue against them, saying that this was another fine-tuning problem. So I just wanted to know which of the particular things you talked about would evade these theoretical arguments.
Thank you. So the main one of the main conceptual points here in my presentation was the difference between scenarios where you break Lorentz invariance and scenarios when you deform Lorentz invariance. Some studies, there were also other studies. Myers was one of these studies. Let's check. Anyway, I should have more references on these slides. But anyway, there are several studies that have observed that if you break Lorentz invariance, basically renormalization is screwed up and you need very high fine-tuning in some sense, very simple-minded description. Results do not apply to the deformed symmetry case, but on the deformed symmetry case, what applies is that we are still learning how to do, there are proposals, but we are in the phase of understanding still what is the correct way to do field theories with these deformed symmetries. So quantum field theory with broken Lorentz invariance have this fine-tuning problem. Some will claim. I'm generally speaking, yeah, then you can answer, but I'm generally speaking because as a phenomenologist, however, and actually, as you might know, I have been a strong advocate of the deformed symmetry scenario on the conceptual side. But as a phenomenologist, fine-tuning, I mean, I see so much fine-tuning in the universe. So an argument that disfavors the phenomenology on the basis of fine-tuning, doesn't impress me. But for the more formal theories, an assessment is that there are claims, and Nick Mavromado will argue against it, but there are claims at least that quantum field theory with broken Lorentz invariance requires high level of fine-tuning. For deformed relativistic symmetries, there is no such claim, but maybe it's just because we still don't know really how to do quantum field theory. So in both cases, quantum field theory is a challenge, but in neither of them is a challenge that should discourage a phenomenologist, because fine-tuning is what? Is a perversion. And not knowing how to do something is not a good reason not to do phenomenology. It's a different mindset with respect to more formal approaches. Will let me?
Yeah, maybe you will let Nick comment quickly, or do you have more questions there?
There is one more question here.
Yeah. Okay, so maybe you go first and then Nick.
Well, my question will be the following. What are the criteria to choose the dispersion relations to be tested? That is, of course, the main criterion is that in some limits they should reproduce the usual Lorentz invariant ones. But besides of this evident criterion, what are the possible ones?
Well, actually this is easy. The answer to this is easy. Let me do it in flat space time so that I really know. So, for example, so the first answer is it must disappear when you take the Planck scale to infinity. And what you need in phenomenology, in this phenomenology, you don't need the exact formula. You just need the leading order correction. This is very interesting for formal physicists because how do you know it's the right formula? But for phenomenology, you don't need the right formula because we will be so lucky if we catch the leading order. So what I'm writing in my slides do not have the presumption of being actually in the toy models that I prefer, like this Kappa-Minkowski space-time, we can constructively compute these modification to near shallowness and time delays, and they depend on an exponential of the ratio between energy and the Planck scale. But this exponential appears in the formula in such a way that when you take the leading order, it's actually a linear term. So the criteria, of course, is that the effect must disappear in the limit of Planck scale going to infinity. The idea to be understood by more formal theorists is that we only need the leading order. A phenomenologist will not pay attention after you give a formal talk and you show me the leading order. Then you say, but now I show you what the exact formula is. I will go get a coffee when you show me the exact formula because I cannot test it. It's intestable. You know, the only chance we have is to test the leading order. And the leading order we are assuming is the leading order of an analytic formula. Of course, you could have worse things, but we're assuming the leading order is an analytic formula, so we are assuming the leading order will be some power of E over E Planck, as you see in these formulas. And again, all the models we are able to actually constructively analyze, they give this, they give analytic corrections which have a leading order which is either E over E Planck or E square over E Planck square. So we don't make any selection, really. We don't need to do one advantage of this phenomenology, which is desperate. You know, we are looking for such small effects, which is always a disaster, but is an advantage because we don't have to actually choose formulas. Because when you only need the leading order, you will test all the leading orders you can test, independently of who proposes who.
Okay. Can we do one last question from you?
From there, yes. Then we should move on, but yes, one quick one probably.
Okay.
Very simple one. What about diffeomorphisms? Is there some type of effective action that produces these effects, and that is diffeomorphism invariant, or do you simply give up diffeomorphism symmetry?
No, the idea is not to give up with the diffeomorphism invariance. It's just a tough topic. So what we need here is some sort of, and the only example that I have seen myself worked out to the level of detail for me to make sense is non-commutative geometry. But what we really need is a notion of like a generalization of Riemannian geometry, where locally, instead of being locally Minkowski, is locally quantum Minkowski. And what we all think, I mean, I don't know of anybody who would give up diffeomorphism invariance in the quantum space-time research, is not that we want to give up diffeomorphism invariance. Surely we will not have classical diffeomorphism invariance, but we probably are dealing with quantum geometries, and so we need a new notion of deformed diffeomorphism invariance, which applies to geometries which are quantum curved in some sense, and what is clear to us is that it must be locally not Minkowski, not classical Minkowski, but some quantum Minkowski. So quantum Riemannian. I don't know if this makes sense, but we will discover that surely we are not giving up diffeomorphism invariance, but we are not imagining classical diffeomorphism invariance to be compatible with this. If we have locally quantum Poincaré or quantum de Sitter, to have the quantum group Q de Sitter applied to constant curvature geometries, then we will have some quantum version of diffeomorphisms applying to this. There is some research, I think the West group in Austria did some work on this when West was alive. There are some works on this idea of a deformed diffeomorphism, kind of a quantum group version of diffeomorphisms, but nobody has gone far enough for me to say that there is a compelling candidate. But what I can reassure you that we do expect diffeomorphism invariance, some form of diffeomorphism invariance to arise.
I think Nick wanted to comment very quickly, and then we can move on quickly.
Well, I will. First of all, as an early comment, do not mix, please, the DSR with the modified special relation. You may have spontaneous breaking of Lorentz symmetry through background, which we have, which is perfectly, you can construct an action which is the Fermat's revised, but the background breaks. Now, I want to come back to this renormalization group argument. This is incorrect. In condensed matter physics, you have an explicit breaking of Lorentz invariance, and of course, there is no fine-tuning, right? So in any condensed matter system, you have the Debye frequency, which is whatever you would call the ultraviolet cutoff. The speed of light is the sound speed, but then the system is not a relativistic environment. The mistake that they claim on this is that they did Lorentz invariance renormalization argument to a non-Lorentz invariant or spontaneously broken theory. That's what I wanted to say. And to finish, the cutoff, since you mentioned the Clearance and Jacob formula, if the cutoff, if you break Lorentz invariance through defects, as we did it originally, then the factor 1 plus z is not there because you have a redshift-dependent density of defects, which because it's a linear defect cancels it. So there are more general formula, as you said, than this. This Jacobian assumes a constant ultraviolet cutoff for gravity. That's what I wanted to say. And to answer Christoph's better question, yes, there is the form of invariance if there is spontaneous breaking of Lorentz symmetry. That's all I mean.
Thanks. You want to say something, or we should move on, in fact?
Yeah, I think we need to move on here. So let us thank Giovanni once again.